Welcome to a refresher lesson for rational functions graphing. This video corresponds to the examples on a worksheet packet that can be found at my Teachers Pay Teachers store. In this video, I will explain the skills and steps necessary to complete all of the examples on the worksheet. Please feel free to skip around to engage in the concepts with which you would like some help. So when we are talking about graphing of rational functions, they can be a bit tricky sometimes. So we want to take a very organized, thoughtful approach to this. And we're going to use 4 major characteristics of rational graphs to help us graph them. The first is to determine where do I have x values that make the function undefined. So a rational function is simply a polynomial over another polynomial. Okay, as long as the polynomial in the denominator is not equal to 0. Okay, and so we need to think about what is this polynomial and what are the x values that would make it equal to 0. And if there are any, that is one of the first things that we want to include in our graph. And the way we're going to include that is either with a vertical asymptote or with a hole. And so to decide, you first need to start by factoring the numerator and the denominator as much as possible. So that's step number 1. And then you're going to determine which values of x make any of the factors in the denominator equal to 0. Okay, so you're going to identify what those values are. Then you're going to simplify that rational function by canceling any common factors in the numerator and the denominator. So if you happen to have something that is in both the numerator and the denominator, you're going to cancel that out. Okay, and you're going to, after you do that, you're going to note which x values made the denominator equal in the simplified form. So in this new simplified form, if you were able to cancel anything out, what are the values that make the denominator equal 0? And at those x values, you're going to put a vertical asymptote. Okay, now because this is an x value that makes your function undefined, you can never cross an vertical asymptote. Because if your graph crosses this vertical asymptote line, what you are saying is there is a value of x that will give you a value of y that will give you a point on this graph. But you've just identified that value of x as making the function undefined. So if you draw a vertical asymptote, you can never cross over vertical asymptotes. Now, what about those factors that got canceled out? Well, at those, whatever x values make those canceled factors equal 0, instead of putting a vertical asymptote, you are actually going to put what we call a hole, which is literally a little circle that looks like a hole. And you're going to take that x value that would make the canceled factor 0, and you're going to substitute it into the simplified version of the function, because you will get an answer from that. And so whatever that XY combination is, you will put a little open circle at that particular point to represent a hole, which again means you cannot have a y value at that point because in the original function, it would make the function undefined. Hopefully that will all make more sense when we see an example. But that is a really huge characteristic about rational graphs that other graphs don't have, is this idea of a vertical asymptote or a hole that indicates where x values make the function undefined. And that's one of the first things that we will identify as we seek to graph rational functions. Then we want to think about end behavior. Excuse me. End behavior is exactly what it sounds like. It's what's happening on the quote unquote ends of the function. So a lot of times we see this notation of, as x is getting really big, increases without bound, approaching infinity, however you want to say that, then f of x or y is approaching something. Now, it may also be going to positive or negative infinity, or it could be approaching an actual value. Okay. With end behavior, if we draw any kind of asymptote to indicate that our graph is going to be approaching a particular value, we need to realize that these asymptotes can be crossed in what we might call the middle of the function. Okay, so if we're in the middle of the function and we happen to cross the asymptote, not a big deal. As we get out to the ends of the function, then these asymptotes are going to kind of show us what the behavior of the graph is going to be doing. Okay. And there's really three different cases that can happen depending on the degree of that polynomial again that's in the numerator and the polynomial that's in the denominator. So if the degree of the polynomial in the numerator is less than the degree of the polynomial in the denominator, then as x gets bigger and bigger or smaller and smaller, so as you go farther and farther to the right or farther and farther to the left, approaching positive infinity or approaching negative infinity, your graph is going to be approaching 0 for y values. Case number 2, if the degree of the polynomial in the numerator happens to be equal to the degree of the polynomial in the denominator, then as x approaches either positive infinity going farther and farther right, or negative infinity going farther and farther left, our function is going to approach some value. And that value is going to be a over b, where a represents the leading coefficient in the numerator's polynomial, and b represents the leading coefficient in the denominator's polynomial. So you just take that a over b fraction, whatever value that is, and that is the value that our y values will be approaching in this case. In the third case, if we have the degree of the polynomial in the numerator being bigger, greater than the degree of the polynomial in the denominator, then we don't have a horizontal asymptote anymore. So in case 1 and in case 2, whatever, whether we get a 0 or an actual value to be approaching, that establishes a horizontal asymptote that we're going to be getting closer to. In the third case, we end up with what's sometimes referred to as a slant asymptote, and you get that by actually dividing the numerator by the denominator to see what you get for an answer. And the end behavior of your rational function will follow the same kind of behavior as the quotient you get from dividing. Okay, again, I hope this will make a lot more sense once we see a couple of examples. Two more characteristics that are going to be really helpful for us are going to be the x and y intercepts. Obviously, with the y-intercept, you're substituting 0 in for x to get the result. A real easy tip for this is that it's going to be the constant of the numerator over the constant of the denominator, because every other term has an x, and putting 0 in for x will wipe it out. Excuse me. Do take note that if x equal to 0 is one of the values that made the rational function undefined, then the graph will not have a y-intercept. So if you happen to have a hole at x equals 0 or a vertical asymptote at x equals 0, then you will not have a y-intercept in that graph. For x-intercepts, obviously it's the other way around. It's putting 0 in for y and solving for x. But again, because we're dealing with a rational, where we're putting in 0 for y, we have a polynomial over a polynomial. We know that the only way this becomes 0 overall is if my numerator becomes 0. Because 0 divided by anything other than 0, so again, q of x cannot equal 0, but a 0 divided by anything else is going to give you 0 for an answer. So the tip here is that you really only need to set p of x equal to 0 to find where your x-intercepts are going to be. All right, so let's put all of this into practice. Here's our first example. Want to graph the function f of x equals x plus 1 over x squared minus 4. Okay, so very first thing I would recommend is that you're going to factor anything that you can in the numerator or the denominator. Okay, so I can't really factor anything else in the numerator. Actually, let me do this really quick. I'm just going to write this. Off to the side, maybe. I can get this to work. Well, that's not what I wanted. There we go. Now we're back. Okay, so off to the side here, I'm just going to rewrite this. Our x plus 1 cannot be factored any more than that, so it stays x plus 1. Our x squared minus 4 can be factored into an x plus 2 and an x minus 2. Okay, so looking at this, we realize based on the denominator that we cannot have x equal to a positive 2 or x equal to a negative 2. Which means that our vertical asymptotes, because we don't have any factors in common between the numerator and the denominator, so our vertical asymptotes are going to be the equations, the vertical lines, x equal 2 and x equals negative 2. Okay, now I'm going to hold off starting to put this on the graph until I've gone through all 4 of those characteristics that we just talked about, and I'll show you why in just a second. All right, next, let's take a look at end behavior. So with end behavior, we're looking at the degree. So I have a first degree polynomial in the numerator and a second degree polynomial in the denominator. That means that when I go back to looking at end behavior, we are looking at case number 1, where my degree in the numerator is less than the degree in the denominator. Okay, so degree of the numerator is less than the degree of the denominator. And that means that my f of x is going to be approaching, whoops, sorry, 0. Okay, so that's what end behavior is going to be doing. Then I'm going to look at the y-intercept. So I can either substitute 0 in for x and work it out, or I can just realize that when I do that, all I end up with is just constant over constant. So my y-intercept is going to be at a negative 1/4. And then finally, we're going to look for x-intercepts. And so the x-intercept comes from taking the numerator and setting it equal to 0. So that means x is going to be a negative 1. All right, so now as I start to put all of these things into my graph, I kind of want to take a look at the types of numbers I have to see what kind of scale I want. So it looks like in terms of x's, going with a scale of 1 is going to be just fine. In terms of y's, I do have this negative 1/4 here, which is going to be really hard to graph if I go by a scale of 1. So I think I'm going to go on a scale of 1/2. So actually make this a 1, this a 2, this a 3 on the negatives, 1, 2, and 3 on the positives. Okay. If you want to leave it as just ones, that's fine. Just, make sure that you're choosing something that makes it easy to graph. Okay, so first of all, we have our vertical asymptotes at +2 and -2. Asymptotes should be drawn as dotted lines because they are not actually showing you the function. They are giving you guidelines for the function. So at +2 and at -2, I'm going to draw a dotted line to show where my vertical asymptotes go. For my end behavior has f of x approaching 0, so I'm going to have a horizontal asymptote here at 0. Okay. Then I have my y-intercept at -1/4, so now that's going to be right there. And I have an x-intercept at -1, which is going to be right there. Excuse me. All right, now, once you have all of those things added to your graph, you may still need some test points. So for example, when I look, I have a couple of points that are in between my two vertical asymptotes, so I'm getting an idea of what's going to happen with the graph in that section. But I don't have any indication of what's happening to the left of my vertical asymptote or to the right of my vertical asymptote. So I'm just going to pick some x values to put in and see what I get for y. So for example, if I choose -3 for an x value, when I put in -3, I get -3 plus 1 over -3 squared minus 4, and that gives me a -2/5. Okay, so at -3, I have a -2/5, which is going to be somewhere right about, oops, not there, there. Okay, and I'm going to do the same with +3. I have a 3 plus 1 over a 3 squared minus 4. And now I'm going to get 4/5. So for positive 3, I'm going to get something right about there. All right, so here's one of the tricks to graphing rational functions. The outside corners. So what I mean is the sections that are farthest to the left and farthest to the right usually end up being a couple of corners. And in those corners, you get what I call corner huggers. So as soon as you have a point, you have a pretty good idea which corner you're hugging into. And we're just trying to get an estimate of what this graph looks like. It doesn't have to be perfect. So as soon as I know that I have this point, for example, then I know that I'm hugging into the upper corner, and then I can go ahead and draw a corner hugger that's just going to curve right into that corner. Same thing with this point on the left side. Since that's now in a lower corner, I can go ahead and draw a lower corner hugger right there. And that gives me an idea of how that's going to curve into that corner. If you have a middle section, like we do in this case, usually you're either going to get something that looks a little bit like a U-shaped parabola, or something that looks a little bit like a cubic kind of shelf. Now I say a little bit like because in reality, a parabola or shelf in those cases would expand to the left and the right without bound. We do have them bounded because of the asymptotes, but the general shape is going to be there. And so in this middle section, we can see that we have a point here where we're crossing the x-axis, and we have a point here where we're crossing the y-axis, but we don't have any other point over here where we must have turned back up to make it a U to go back through the x-axis. And so that pretty much tells us, without even needing any other points, that this is going to be more of a shelf shape to fit in between those two asymptotes. Because if it was a U shape, I would have to have another x-intercept for the U to cross back through. And so there you have it. This is the general graph, an approximate decent graph of our f of x function, x plus 1 over x squared minus 4. Let's take a look at another one. So in this case, again, we're going to start by factoring. So 2x squared minus 5x minus 3 will factor into 2x plus 1 and x minus 3. The x squared minus 5x plus 6 will factor into x minus 2 and x minus 3. Okay, so based on that, we can tell that x cannot equal 2 or 3 because those are values of x that would make the factors in the denominator equal 0. But now we also notice that I have a common x minus 3 factor in both the numerator and the denominator. So those two will cancel each other out. And that tells me that I will have a whole when x is equal to 3. So I am now going to take that 3 and put it into the simplified version of my rational function. And I'm going to get a 7 for an answer. So that means I'm going to have a whole at the point 3, 7. Okay, so that takes care of this X value, that means I have a vertical asymptote at the other value, which is X equals 2. Okay, so that takes care of the values of X that are going to make our function undefined. Next, I'm going to take a look at end behavior. This case, I have a 2 for my degree in the numerator. I also have a 2 for my degree in the denominator. So if degree in the numerator is equal to the degree in the denominator, then that means f of x is going to be approaching the ratio of the leading coefficients. So 2 over 1, which is going to be 2. So again, we're going to have a horizontal asymptote at y equals 2. Then we'll take a look at our y-intercept. For the y-intercept, I'm just going to take this -3 over this +6, ratio of the constants. So I get a -1/2. And finally, for our x-intercepts, excuse me, I'm going to take the numerator from the simplified version and set it equal to 0 to get x also equal to a -1/2. Okay. So based on the kinds of numbers we have to work with, again, I think for my x values, I'm okay with going on a scale of 1. So there's 5 and -5. But I have this y value of 7. So I think I'm going to go with a scale of 2 for my y values, just to make sure everything will fit. All right, so I have a hole at 3, 7. So 1, 2, 3, 2, 4, 6, 7. That hole is going to be right there, and I'm going to draw an open circle for that point. I also have a vertical asymptote at x equals 2. So I draw my dotted line here at x equals 2. My end behavior says that I'm going to have a dotted line here at f of x equals 2. Remember, I have a scale of 2, so my 2 is just one box up. Okay. And then I have -1/2 for a y-intercept. So again, with y's being on a scale of 2, that means I'm really close here to my origin. And I have an x-intercept also at -1/2, which means I'm going to be right about there. Okay, so I really don't need any test points in this case because I only have the 4 corners divided up by my horizontal and vertical asymptotes. I can already tell from my x and y intercepts that this corner hugger is going to go through the points like this. So I don't need any extra help with that really. Okay. And because I have the hole up here, I'm pretty sure my corner hugger up here is going to come down, meet that hole, and then continue past that hole and curve into that corner. And there's my graph. All right, one last example here. And in this example, instead of having a horizontal asymptote, we're going to end up with a slant asymptote for our end behavior. So we'll start off the same way. We will factor everything first. So the x squared minus x minus 12 will factor into x minus 4 and x plus 3. The x plus 1 doesn't need any further factoring. So I know that x cannot equal a negative 1. Since there is no common factor in the numerator or the denominator, that means I'll have a vertical asymptote at x equals negative 1. For end behavior, this is a case where the degree of my numerator is greater than the degree of my denominator. I have a 2 on top, I only have a 1 on the bottom. So in this case, I actually need to take my x squared minus x minus 12 and divide it by x plus 1. And because x plus 1 is in an x minus k form, I can do this division either in long division or I can use synthetic division. So I'm going to put negative 1 out here in the box. I'll put the coefficients 1, negative 1, and negative 12. And then do synthetic division. So 1 comes down. Negative 1 times 1 is negative 1. Add, I get negative 2. Negative 1 times negative 2 is 2. Add that together and I get a negative 10. Now remember, in synthetic division, this final number is our remainder. But when we're doing this, since we're just trying to get an idea of what the behavior is going to be, we don't need to consider the remainder. So we're just looking at the fact that we ended up with a quotient of f of x equals x minus 2. And we will actually draw that as an asymptote to guide where our graph should go. Then we'll take a look at y-intercept. The y-intercept is going to be constant over constant. So I have negative 12 over 1, which gives me a negative 12. And then for the x-intercept, if I use the factored form of my numerator, x minus 4 times x plus 3, set that equal to 0, then it's very easy to tell x is 4 or negative 3. All right, so in order to graph this now, I'm again going to use 1 as my scale on the x's. I think I'll use 2 as my scale on the y's to make sure everything fits well. And then I have a vertical asymptote at x equals negative 1. So that's going to go there. Then I have a slant asymptote at f of x equals x minus 2. So that means I have a negative 2 y-intercept, excuse me, and I have a 1 for a slope, which based on the scales I have, going up 1 is only half a box, over 1 is going to be a full box. And again, we just want to do this as a dotted line to show that it's not actually part of the graph. It is just guiding what the graph is going to do. So this is my slant asymptote. All right, so this was supposed to be a negative 12 for my y-intercept. So negative 12 is going to be down here. My x-intercepts are at positive 4, which is right there. and a -3, which is right there. And so again, I don't really need any more points than what I already have. I can already tell sort of the corners that I should be in. It's just that this time it's not right angle corners, they're kind of slanted corners, but you still get the idea. I should be in this section here, going through my points, staying within my asymptotes. And I should be in this section here. Again, going through my points and staying within my asymptotes. And that's the graph of x squared minus x minus 12 over x plus 1. All right, I hope you found this helpful. If you would like to see other concepts that you need to refresh or review, please check out my Gordon Global Math page on YouTube. Videos covering Algebra 2 and pre-calculus concepts will be added throughout the spring of 2025. Thanks for watching.